Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're going to still stay on the topic of thermodynamics, but we're going to go beyond the pure substance analysis, and we're going to deal with the change in closed systems. So the idea is that once we mastered how to grab properties, figure out properties, define states on pure substances, what we want to do now is be able to understand what is needed to change from one state to the other. So a lot of the approaches are going to be exactly the same as in the previous sections, in the previous problems, but now it requires you to have that understanding prior to being able to solve these problems. And in this case, the statement reads, a 0.5 meter cubed rigid tank contains R134A, initially at 160 kilopascals and 40% quality. Heat is now transferred to the tank until the pressure inside rises to 700 kilopascals. Determine A, the mass of the refrigerant, and B, the amount of heat transfer that are to be determined. Oh, that was a horrible sentence. So determine the mass of the refrigerant and the amount of heat transfer. Also show the process on a PV diagram. So let's analyze the problem. First thing, we have that magic word rigid tank. What does that tell us? It tells us that the volume of the tank will not change regardless of how much heat we give to it, right? So the volume is going to stay constant. What else? We're dealing with the refrigerant 134A, so watch out when you go for the property tables to look at the right table. Don't grab water, don't grab air. We have to grab the one for the refrigerant, right? Freon. And if you don't know what Freon is, we did one of the videos, we actually introduce it and talk about it here, so you can check it out. Initially, it's 160 kilopascals and 40% quality. So note that we have two, properties. I'm not sure if quality can be understood as a thermodynamic property, but it allows us to completely define the first state. So the first state is completely defined. We have 160 kilopascals and 40% quality. So what we know here beforehand is that the first state is a saturated mixture, right? And know how all these things you need to know beforehand to be able to solve this problem. That's why, it's the next step after the ones we've been doing on the previous couple weeks. Heat is now transferred to the tank until the pressure inside rises to 700. So we have this bit of information here for the second state, in addition to the idea that the volume in the second state is 0.5, right? Mass of the refrigerant and the amount of heat transferred. Okay, beautiful. So I'm going to start by drawing my little boxes that I always do. And this is going to be my state number 1. And we have R134A. And the volume 1 is 0.5 meters cube. What else do we know? We know that inside this guy we have 160 kilopascals. And what I'm going to do is I'm going to copy this across, because everything's going to be the same except for the pressure. So let me remove this pressure here. This is not the same. This is now 700. Okay, this is we're going to call state 1. This is my state 2. Now from here to here we add heat to the system. Okay, and we can see that what is happening is that the pressure is rising. Temperature is most likely rising too. We need to look at that later. But what do we know about the first state? Well, we know the quality is over here. We know the quality is 40%. What does that mean? It means 40% in mass of the mixture here. We know it's a saturated mixture. We know 40% of the mass is vapor. The 60% of the mass is liquid. Okay, so if I want to now know what is the mass of refrigerant, so we'll put it a mass of 134A. That's my first question. Well, that's going to be a combination of the mass of liquid that I have, liquid that I have inside, plus the mass of vapor, right? And to be able to find exactly what is the total mass, that is the sum of the two, what I need to know is, okay, what is the mass of liquid? What is the mass of vapor? So I need to know these two guys individually. Okay, and to do that, what we're going to use is the idea of specific volume. As you know, this is one of the thermodynamic properties, right? In this case, because we know it's a saturated mixture, it's going to be a combination of both the specific volume of the saturated vapor and the specific volume of the saturated liquid. Okay, and all these things we know already from prior problems, right? From understanding how pure substances work. So in this case here, it's just the saturated vapor times the fraction of saturated vapor that I have, which happens to be the quality. And in this case here, whatever is not saturated vapor, that is 1 minus x times my saturated liquid. So what I need to do is I need to find these two guys. This is my game plan. Find these two guys. With those two guys, I can find the V mix. With the V mix, then I can go ahead and say, okay, so if the saturated, the specific volume for the mixture is just a volume divided by the mass of the mixture, then that means that if I want to find what is the mass of the mixture, remember the mass of 134A, all I need to do is I need to take that volume and divide by the specific volume of the mixture. Okay, I happen to know this is 0.5. So if I find this guy here, the one in blue, this guy, then I'm good to go. All right, and how do I go about finding these two guys here? Well, I know that we are at 160 kilopascals. So I'm going to go to my pressure table on the saturated mixture for the R134A, and I'm going to grab the value for VSAT liquid, VSAT vapor, as simple as that. This one here is saturated for 134A. However, this is the pressure table, so no good for us. So we keep going, scrolling down all the way into the pressure table. These tables are available for you on the description of the video down here if you need them. And so this is saturated, good. This is 134A, good. This is pressure, good. 160 is right here, so I'm going to highlight this for our sake. And I'm after the saturated liquid specific volume and the saturated vapor specific volume. So I'm after these two values here, this guy and this guy. Okay, so with those two guys, that's all I need really to be able to solve that first part of the problem and then find out what is the mass of the mixture. So let's do the here on the corner so we can have access to those numbers there. So the mix is going to be 0.12355 times my quality, right, which is 40, plus 0.000007435 times whatever is not the quality. So this is quality 40%, or 0.4, you can put it either way. And here 1 minus, or 100 minus 40%, so 60%. Okay, so this, we do this math here, and we end up finding that the specific volume for the mixture is 0.04986. Unit has to be exactly the same unit as these guys here because I'm not changing anything. I'm just multiplying by a ratio, right? And you can check the unit here, meters cubed per kilogram. And what I can do now is I can grab this value and I can happily go back up there where we had our, we lay down the equations. So this is the answer to this part. So therefore, this is the mixture one. And here what we can do is, okay, so the mass is just going to be 0.5 divided by the 0.04. There you go. All right. This is meters cubed, so meters cubed and meters cubed go away. We're left with kilograms, which is unit for mass, which is great. And we find that the mass of the mixture is 0.03 kilograms. Okay. Now, if we wanted to find what are these individual fellows here, what we can do is that very simple. We just multiply the 1003 by 40. Right, so if you multiply this by 40, we're going to get 4. So it's about 4 kilograms of vapor and about 6 kilograms of liquid in this mixture. All right, so this is part A, the answer for part A. Cool, what else? B, what's the amount of heat transfer? Okay, so how much heat here? How much heat do I need to give to the system so that it can go from the 160 kilopascals saturated mixture to the 700 kilopascals. So how do we know that? Well, now we start to use the first law of thermodynamics, and this is where, this is, I guess, the biggest change, because before we didn't think about this. And the first law of thermodynamics tells us that energy cannot be created or destroyed. It can only be transformed, right? So in this case here, the internal energy, the change in internal energy has to be equal to the heat given or taken away from the system, plus or minus the work done to the system or by the system, right? In this case, the volume did not change, right? My delta V, delta volume, put it like this, delta volume is nil, right? Why? Because we knew from the start that V1 and V2 are the same because the tank is rigid, right? Rigid tank, V1 equals V2. If there's no change in volume, because we know that definition of work is the integral of pressure in respect to the volume as we go from volume 1 to volume 2, that means that work is nil too, right? If there's no change in volume, then there's no work being done. And if that's the case, then this guy goes away, and it means that the change in energy, internal energy, has to be the source of the heat, okay? In other words, all the change, if I can find what is the initial state of internal energy and the final state of internal energy, the difference between the two has to be the heat that was given into the system, right? So if I can find U1 and U2, I can find the difference between the two, and I can find what was the heat given to the system. So that's very straightforward. In the case of U1, right, in state 1, internal energy, we know it's a saturated mixture. And we can do exactly the same thing we did for the specific volume, exactly the same thing. I'm going to do the internal energy of the saturated vapor. I'm going to multiply that by my quality, which is the fraction of saturated vapor that I have. I'm going to get the one for the saturated liquid, and I'm going to multiply by whatever is not vapor. And we know exactly that. This is the 40, this is the 60. All I need to do is grab this value and this value off the same row that I was before. Where was I? Here I was. So all I'm looking for is now, instead of specific volume, I'm looking for internal energy. That's all I'm looking for. The saturated liquid one and the saturated vapor one. Okay, so we have 31.06 and 221.37. And by the way, this number here in the middle, right, this is actually the difference. So if you take the 221.37 and subtract by the 31.06, you get this difference here. And the reason for that is that you can simplify your math if you use the difference between the two instead of using each individually and then combining them. So feel free to do that. It's up to you. I'd like to do it the way with both of them because I think it's more intuitive if you're looking at this for the first time. But you can see that if you take this value here, you're going to get, if you multiply this guy by x, you're going to get the negative there. And you're also going to have the same thing here. You're going to get the u sat in x. So there you can put x in evidence. You're going to have 1 minus x, or sorry, 1 minus the difference between the two. And you just need to use that difference between them, all right, which is already in the table. But without complicating things much, let's go ahead and plug in these values. So in this case here, we have 221.37, and I'm multiplying that by 40%, or 0.4, same thing, right? Plus, what is the saturated liquid one? That is 31.06. And I'm multiplying that by the 60%, or 0.6. Okay, and this renders about 107. So 107.184. And the unit is the same unit of the table, kilojoules per kilogram. All right, now note that this is always a combination between two things. There's only two possibilities. It's always liquid or vapor. So our final value needs to fall between these two numbers here, right? So 107 needs to fall necessarily between 221 and 31.06. If it doesn't, you did something wrong on the math. So just jump a few steps back and you can figure out what you did wrong, because it surely was something in your math. Now, what about U2? Okay, what about U2? Well, we don't know much about the second state other than the fact that the pressure is 700 kilopascals and the volume is 0.5. But because now we know the mass, that means that if no mass left here, right? So there's no mass leaving from one state to the next. Then that means that the second state also has this mass here. And if it also has this mass, then that means that my specific volume has to be the 0.5 divided by the same mass, which is going to give me exactly the same specific volume that we had before, right? So in other words, if you wanted to do the full way around, you'd go, okay, specific volume of state 2 will be the volume of state 2 divided by the mass of state 2. In this case here, this is 0.5, and this guy here is a 10.03. So this also gives me the, what was the number again? Forget 0.04986. right? And this is meters cubed per kilogram. Brilliant. And then if that's the case, I know two things now. I know the pressure, which is 700, and I know the specific volume. So what I can do is I can now jump into the table and I can look for whether this is going to be a saturated mixture or superheated or what's the case here. And then we can go from there. So I'm going to go back into where I had my highlighted row at some point. Was it close to where we were? No, temperature. Here you go, pressure. Now instead of 160, I'm interested in 700. So I'm going to go down here. This is what I'm looking for. And I'm interested in knowing in this column here where my number falls, right? So I have the 0.0008 and I have the 0.029. And I want to know, my question is, my number of, where is it? 0.04985. Does it fall between these two guys here? Is it greater than this guy here, or is it smaller than this guy here? Well, it's definitely greater than this one, and it's greater than this one here. Okay, so that indicates to me, okay, this is not a saturated mixture. This has to be a superheated fluid, right? So we can say, because specific volume 2 is greater than the saturated vapor specific volume, then therefore this is a superheated fluid. So I'm on the wrong table. This is not the right one. I need to scroll down all the way until I find the superheated one for the refrigerant. Okay, and I'm looking for 700 kilopascals, so that's 0.7 megapascals, same thing. So I need to scroll down all the way until I find the 0.7 right there. And now what I need is a specific volume that is 0.049. And I'm going to note that it's going to be, my temperature is going to be actually greater than the 160, right? So it's actually greater than the value that I have here. It's quite close to this 160, but it's greater. Okay, so what do I need to do in this case? Well, in this case, because it's so close, I can extrapolate without causing much issues, right? So what I'm going to do is I'm going to say the following. My specific volume, well, let's put it like this. My specific volume, and I'm after my internal energy for 2, right? So my specific volume in state 2 is 0.04985. The one that we have on the table is 0.47306, and that corresponds to a internal energy of 357.42. And the other one I have is 0.048597, and that one corresponds to 367.31. So what I want to say is, okay, let me assume there's, as we do in every single, I'm going to do the same thing we do on interpolation, except I'm going to extrapolate. If you have trouble, there are other videos here on the channel to talk about interpolation, okay? So I have, let's put here specific volume, and here we have internal energy. So I have one value here, and I have a second value here. All right, so this is, I don't know, the 0.47, and this is the 0.48. And here I have the 357 and the 367. Okay, and they've matched like so. And I have another value, which is the 49 over here, which is what I'm looking for. And I'm going to say, oh, let's just pretend that between these two guys, the way that the internal energy behaves is just a straight line. So I'm going to extrapolate to find what would be the value here for internal energy. Okay, and we can do exactly the same process you do in interpolation, whether you use a spreadsheet with Excel, if you use a calculator, if you want to do it by hand, all again on the video that we've previously tackled here in the channel. And then what we get is the value for the extrapolation here is 376.9. Okay, and that would be the value that I'm looking for U2. So let me go ahead and copy this. And let's check it all the way up again. Where were we? Here we are. Okay, so now we have the value for U2. And if you recall why we're doing all this, because we want to find what is the delta U, right? What is the difference in internal energy? And we're going from our 376.9, and we're coming from the 107.184. Both are in the same units, kilojoules per kilogram, so we can subtract that without any problem. And what we find is that this difference is about 300, and so it's approximately here, so 269 and 69.7 kilojoules per kilograms. We know the mass, right? We know the mass. The mass is about 10.03, so I can multiply that difference by the mass. So we'll do delta U times the mass, and I'm going to get the uppercase one, which is just, and this is going to be just about 10 times greater, so 2705.3, and that now is in kilojoules, not in kilojoules per kilograms. Okay, so we did all this because we know that, if you recall from our analysis, we know that the heat given to the system has to be the same in magnitude as the difference in internal energy. And we just found that difference in internal energy is 2700 kilojoules. So therefore, the heat given to my system has to be equal to 2700 kilojoules. Right? And that's my answer there. Note that there's a small yet important step from here to here, right? So if you were to stop here, you may get the question wrong. You may get a half right, because you did find the value, but you need to ensure that you understand that what you're looking for is the heat, and the heat is only the same thing as the internal energy, because there's no work involved, because there's no change in volume. So that extra step is quite important, okay? So what we conclude from this one, if we go back to our original drawing, if you recall, right, we're going from state 1 to state 2, okay? We're going from a pressure of 160 all the way to a pressure of 700, and to do that, we're given some heat to this refrigerant. And the amount of heat that's given to this refrigerant is exactly 27, or approximately 2700 kilojoules, because we know that it has to be the same as the difference in internal energy. And the last piece of the puzzle is to show this on a PV diagram, So pressure and volume, that's a bit different from what we did in the past. But there's no mystery there. What we're going to do is we're going to go do a slightly straight line upwards, slightly straight line on the horizontal. Pressure here, specific volume here. We're still going to have the dome. It's still going to show up very similar to what it was before. And if you recall, we start state 1. We found out state 1 is a saturated mixture. We knew that from the start because it had a quality. And we found out that state 2 is a superheated fluid, right? Superheated fluid. So therefore, what's happening is I'm starting, okay, inside the dome, and I'm ending outside of the dome. But not only that, but I'm doing that without changing my specific volume whatsoever. So that means that I cannot travel horizontally here. I can only travel vertically, okay? So that means that if I want to draw, what I can say is, okay, I start here, this is my point 1, and I go upwards because I'm increasing my pressure, remember, and I end here, right? I need to end out of the dome somehow. If I do a dome that's a bit nicer to myself, I can do something like this. It's easier to draw what I'm trying to draw, right? So let's do this. Okay. What do we have over here? We have that this point here is 160 kilopascals. And then over here we have this is 700 kilopascals. And over here we have the 0.049 something, right? And that's meters cubed per kilograms. Okay, that would be our PV diagram right there. Now, if we wanted to draw, we can draw, our isothermal lines. So we have an isothermal line kind of like so. We don't need to do that. All we need to do is to have this kind of drawing there, and that is perfectly fine. Okay. If you have any questions, as per usual, just leave them down below in the comment section. If this video helped you out, consider liking it, and we'll talk soon.